Now let's understand the functional block of the SPI peripheral in a microcontroller. So let's again go to the reference manual of our microcontroller and browse through the section SPI. Here, this section actually describes the functional block of the SPI hardware. If you are having a different microcontroller, then also the functional block looks almost similar. So if you can understand this, you can understand the functional block of your microcontroller too. You can see from this block diagram that 4 pins are coming out: MOSI, MISO, clock and NSS. NSS pin is for slave select. When this block acts like a slave, then the master has to pull this pin to low. After that, the heart of the block diagram is a shift register associated with 2 buffers. One is a TX buffer and another one is a RX buffer. Since SPI is a full duplex communication protocol, having 2 buffers is a must. You can see both TX as well as RX buffers are accessible over the bus, which is APB1 or APB2. To transmit the data has to be written to the TX buffer over here, whose content will then get loaded into shift register and transmission begins. When the shift register receives one complete byte, it will transfer it to the RX buffer so that you can read it. If you observe here carefully, you can see if this is a master, then data is shifted out from this end over MOSI line, and data will be shifted in through this MISO line. After that, we have here a couple of control registers, CR1, CR2, which are used to control the SPI operation, and one status register which holds the status flag of various events which occur during the SPI communication, like TX event, RX event, error event, etc. The clock is produced by the baud rate generator block, which is controlled by these bits in the control register. We'll talk more about these registers in the later videos.